In the previous video, we determined the relation between the coordinates x mu of any inertial reference frame 1 and the coordinates s mu prime of any other inertial reference frame 2. This relation has to be of the form x mu prime equal to lambda mu nu x nu plus a mu according to the principle of special relativity, where this a mu is a space-time translation and this lambda mu is a Poincare transformation that satisfies the special property that preserves eta. That's a property that we can write in this way. Eta mu and then nu sigma equal to eta rho sigma. This is by definition of Lorentz transformation. Now, our task in this video will be to relate the components of this a mu and lambda mu nu, or to interpret them in terms of physical parameters that tell us what is the relative motion and position of the systems of the inertial reference frames 1 and 2. In order to simplify this task, we are going to decompose this generic or general Poincare transformation into simpler transformations using the transformations that we know. So this is the most general Poincare transformation, but we know what a space-time translation is. We know its physical interpretation, and this is a Lorentz transformation, but we know, or we should know, that part of the Lorentz transformations are just space-time rotations of the spatial axis. Spatial rotations of the spatial axis x1, x2, and x3. So we are going to use these transformations whose meaning we know in order to simplify the problem and to reduce it to the transformations whose interpretation we don't know. Basically, these are the transformations between two reference frames that move at a constant speed, and the transformation related to that speed. Spatial rotations are not related to any relative speed, and the space-time translations are not related to any relative speed either. They are related only to different positions, relative positions. Okay, these irreducible Poincare transformations, the one that we cannot further simplify by using rotations or space-time translations, because they are neither rotations nor space-time translations, are what is called Lorentz boost. So we are going to identify the components of lambda mu nu for a Lorentz boost. Okay, so the setup is that the system 1 has its three spatial indices, okay, at a given time, a spatial axis, in this position, for instance, and the system 2 has its three spatial axes in a different orientation, and on top of this, it is moving with the speed v, measured in the coordinate system 1. Okay, the origin will be O, and the origin of this one will be O prime. Okay, since it is moving in this direction, we are going to make some simplifications using, first of all, spatial rotations. So we want to rotate this system 1, in such a way that v will be only v1, 0, 0. Or in other words, that the axis x1, or the new axis x1, will be parallel to v. This is not enough for us, and then we will make another rotation of the system 2, so that the axes of this system 2 are parallel to the axis of the system 1. So after these two operations, we will see something like this. Okay, this will be the axis, the new axis x1, that maybe I will call something different, x2 and x3, and the axis x1 prime and x2 prime and x3 prime after this rotation will be also parallel, and the velocity v will be parallel to x1 and to x1 prime. Okay. A third simplification that we are going to do, and this is achieved by a space-time translation, is that we are going to make O and O prime coincide at t equals 0. Only at t equals 0. So at t equals 0, if the axes are parallel and they coincide, then they are parallel and the origins coincide, then all the axes coincide. So we will have that at this moment that this is equal to x1 prime, this is equal to x3 prime, and this is equal to x2 prime, and O will be equal to O prime. Now, how do we do this? Okay. The first step, we are going to go from 1 to 1 prime, if you want, and from the coordinates x1, x mu, to coordinate y mu, which will be related to x mu by some Lorentz transformation, which will be a rotation. This rotation is chosen so that this speed v is parallel to x1. Of course, we don't change v. V in space-time has the direction it has. We cannot change it. Okay? We would be changing the physics. We only want to change the description of the physics. Okay? And the description is that this v only has a component v1 instead of a general component. But in space-time it is clearly the same. Okay, system 2 will also be rotated to 2 prime, as we said, but by a different rotation. So we have an r prime that relates y mu prime and x nu prime. And what this transformation does is that all rotates this system 2 so that the axes are parallel to those of the system 1. Okay, now we can invert this transformation. This is a Lorentz transformation. Of course, the inverse always exists. Let's call the components of this inverse transformation lambda minus 1 r, and the relation between x mu and y is of this form. So we can replace this x mu in the original formula. Remember that we have x mu prime equal to lambda mu x nu, and now instead of x nu I write lambda minus 1 r nu rho y rho. Okay, this is what I have replaced, but of course I have replaced mu in both sides by nu and this nu by rho in order not to get confused with the indices. Okay, and then we have a mu. Now we multiply this whole expression by this transformation lambda r prime. But of course, since this has an index mu, I have to write the index mu here, and I have to choose a different index, sigma, here. Okay, first I have in the left hand side lambda r prime sigma mu times x mu prime, which is y sigma prime. Here I have lambda r prime sigma mu lambda mu nu lambda minus 1 r mu rho y rho plus, and remember that this lambda r prime sigma mu acts on everything, so you have lambda r prime sigma mu a mu. Okay, this is just a product of Lorentz transformation, so it will be some other Lorentz transformation. And this is a matrix times a vector, so this is another vector that we'll call a mu prime or something like that. The idea, for instance, a tilde mu. Now the third operation is that we go from 2 prime to 2 double prime, okay, defining y mu double prime as y mu prime minus a tilde mu. So if you use this relation here, this is just shifting the origins, so the origin of O prime, so it coincides with the origin of O, okay, but I'm shifting the origins in space, in both space and time, okay, this is important. Then when you replace this here, what you find is that y mu double prime is this product of lambda r prime lambda minus 1 r. Okay, this indicates the product of these three operations. This is what you have here, mu nu y nu, only a homogeneous transformation. And as you should expect, when y is 0, these are the coordinates of the origin of the system 1 prime, y mu double prime is 0. These are the coordinates of the new transform system 2 double prime. We have identified this. Now, if we manage to find the components of this Lorentz transformation, because it is a product of Lorentz transformations, then we will be able to find the original a mu and so on, because we just have to undo all the transformations that we have done. Okay? And these are transformations that in principle we know how to do because they are rotations that do some operation on a space that we know perfectly how to do. We should know at this stage in the master how to rotate two three-dimensional systems. Okay, now we just rotate our paper, so the new coordinate y1 prime is horizontal in this paper. We draw also y2 prime, and at t prime equals 0, or better y0 prime equals 0, we know that O is equal to O prime, and really this coordinates axis coincide. So this is equal to y2 prime and y2 double prime. The moment when y0 prime is not 0, what happens is that you still have here y1 prime and y2 prime, the origin O, but the origin of the other system, O prime, has moved here. Okay, and now we want to find the relation between the coordinates in y2 and y prime and y double prime in this situation, knowing that all the action, all business takes place in the direction y1 and y1 prime. So nothing happens in y2 prime or y2 double prime or y3 prime and y3 double prime. Just because it is customary and otherwise we will be making mistakes. Maybe let's call again our coordinates x1, x2, O, and O prime, and x2 prime. Okay, x1 prime is also coincides, but the origin is here in O prime. This is just a simplification in order to avoid dealing with too many primes. Okay, so we want to find the relation between x0 prime and x0 and x1 prime and x1, because as we said, x2 is equal to x2 prime and x3 is equal to x3 prime. So what do we know about the relation between these coordinates? Well, first of all, it's linear, okay, by assumption. After all these transformations, x0 prime and x1 prime is related by some matrix to x0 and x1. So this matrix will have components A, B, C, and D. Another thing that we know is that the interval will be preserved. And which interval? It is an interval between two events. So one of the events will be the event at which when both origins coincide at t equals 0. So at t equals 0, at the origin, x1 0, x1 is also 0, x1 prime is 0, everything is 0. So if everything is 0, the only thing that remains is the coordinate x1. Sorry, the coordinates x0 prime and x1 prime at a later time, whatever time. And this has to be satisfied. Okay, we know also that when x1 prime is 0, this is the origin of prime. Okay, x1 of this point is v times t. This coordinate system now moves with the speed v in this direction x1. So after a time t, because at time t equals 0, the origins coincide, x1 is v times t. So this is v divided by c. So divided by c x0. So in general, because of linearity, x1 prime is going to be a linear combination of c times x0 times d plus d times x1. And when one side is 0, the other should be 0. So see that this means that x minus v divided by c x0 is equal to 0, which is x1 prime. Now, since the relation between x1 prime and x1 and x0 is linear, the most that can happen that preserves this property, okay, because this is always true, is that x1 prime is some factor, some coefficient to be found times x1 minus v divided by c x0. Now you come here, and this means that this d is this coefficient omega, and this coefficient c is minus omega v divided by c. So this reduces the number of unknowns to just 3, a, b, and omega. Another simplification that we are going to make, but this is just a simplification in notation, and in order to solve more easily the equation, is that we are going to rewrite B as A times Z V divided by C. Okay, so this is just a change of variable from B to Z. And then these linear transformations in terms of these variables will take the form x0 prime equal to A x0 plus Z V divided by C x1, and x1 prime equal to omega x1 minus V divided by C x0. Now we plug these two relations into the equation that tells us that the interval is invariant. And we have a squared x0 plus Z V divided by C x1 squared minus omega squared x1 minus V divided by C x0 squared equal to x0 squared minus x1 squared. Now this is quadratic in x0 and x1, and we just have to compare the coefficients of x0 squared, x1 squared, and x0 times x1, which should be 0. So the coefficient of x0 squared is just a squared minus omega squared b squared divided by c squared, and this is just 1. The coefficient of x1 squared is x squared z squared b squared divided by c squared minus omega squared, and this is equal to minus 1. And the coefficient of x0 times x1, which is 2a squared z v divided by c minus so plus 2 omega squared v divided by c, this has to be 0. We can solve this one first, and we get that this is a squared z plus omega squared is equal to 0, and we use this to eliminate omega squared in terms of z and a squared. So we go with this expression here to these two equations, and we find that this is a squared 1 minus sorry plus z v divided by c squared equal to 1, and here we find that this is just a squared psi squared v squared divided by c squared minus so plus z a squared equal to 1. We take a common factor, a squared z, okay, equal to minus 1, sorry, and to get this 1 plus z v divided by c squared. Sorry about this. Well, v divided by c squared equal to minus 1. You compare these two equations and you find that this is compatible only if z is equal to -1, which is good because otherwise I mean the fact that it is minus instead of plus, because otherwise either omega or a would be imaginary and this would be a big problem. And okay, from this you get that a squared is equal to 1 divided by 1 minus b divided by c squared. Another relation that you find is that omega squared is equal to the same. Okay. So these are the two relations, and if you take square roots and everything, and you re-express this formula here in terms of the values we have found for a, omega, and z, you find that the transformations read x0 x prime 0 is equal to x0 minus v divided by c x1 divided by the square root of 1 minus v divided by c squared, and x prime 1 is equal to x1 minus v divided by c x0 divided by the square root of 1 minus v divided by c squared. And these are the Lorentz transformations, which are irreducible in the sense that we cannot simplify them anymore by using spatial rotations or space-time translations, and they are called Lorentz boosts. Okay. Now we can make a counting of the independent Lorentz transformations and Poincaré transformations that one can make. So there are three possible independent Lorentz boosts, because we can boost means you can go to another reference frame which is related to the other by a speed in three different directions. So this corresponds to 3 parameters, which would be these 3 speeds. And you can also perform 3 independent rotations. So the Lorentz group is characterized by 6 independent parameters. You can also count them in this way. Here you have only one parameter, this v. But remember that we have performed 2 rotations, one on one of the system and one on the other. Okay, each one of them has 3 independent parameters. So you take one rotation, 3 possible rotations on this v. This gives you 3, and then you have the other 3 possible rotations to go to any other general system. So there are 6 independent parameters in the Lorentz group, 3 associated to boosts and 3 associated to spatial rotations. Then space-time translations has 4 parameters, because you can shift the origin of time and you can shift the origin of the other 3 spatial coordinates. So the Poincaré group has 10 independent parameters. Okay, the next thing that we are going to do is to rewrite these Lorentz transformations using a different set of coordinates which are not Cartesian coordinates. These coordinates are called light cone coordinates because they parameterize the light cone, but we will talk about this later. These are two coordinates, x plus and x minus, that are defined in terms of x0 and x1 by this relation. So the 1 over the square root of 2 is just for normalization, and sometimes x plus is called u, and sometimes x minus is called v, although this also depends on conventions. And okay, if you draw these coordinates, so you draw a coordinate system x0, x1, this is a space-time diagram instead of the time diagrams, sorry, the spatial diagrams that I drew before, that only contained x1, x2, and so on. Okay, the coordinate x plus would be here. This would be x plus, and this would be the axis of the coordinates x minus. How do I know this? Okay, you locate the axis x0 at the point x1 equals 0. So you locate the coordinates, the axis x minus at the point x plus equal to 0. So x plus is equal to 0 when x0 is equal to minus x1. Okay, so the points at which x0 is equal to minus x1 lie along this line. So this is the x minus axis, and the other way around. Okay, as you know, this is 45 degrees, and in this space-time diagram, light rays propagate at 45 degrees. So the light cone at the origin, okay, coincides in these two dimensions with just these lines. If you add more lines, another coordinate like x2, which I don't know how to draw, will be something like this. Then the light cone would really be this surface, but the coordinates x plus and x minus lie on the light cone. Okay, the main property of these coordinates is that the interval, which has this form in Cartesian coordinates, now has this simple form. It's just x plus times x minus. The light cone geometrically can be defined. We have defined it like this because I know that you know where the light cone is where the surface or the space in which the light rays that come from a certain point can propagate. Okay, here this is characterized by this formula, as we have discussed many times. This means, okay, with these definitions, that it is either x plus equal to 0 or x minus equal to 0 or both. So x plus corresponds to equal to 0 corresponds to the axis x minus equal to 0 corresponds to the x plus axis, and they cross at the point at which both are 0, which is at the origin. Okay, if I use this form, I see that this means that if I change coordinates, and this change of coordinates is a redefinition of my coordinates, which is not a Poincare transformation, clearly. Okay, after a Poincare transformation, the form of this interval should remain the same. So this is not a Poincare transformation, it's just a change of coordinates. But now I can perform a Poincare transformations in these new coordinates. Okay, Before I do that, let me just mention that if I usually write this as x mu, x nu, eta mu nu, so this is the interval between the origin and some point x mu, then this should be the same. Okay, this means that these new coordinates, let me call them x nu prime, eta mu nu, and now I write prime because it is not the same eta mu nu. This eta, so to clarify what I am saying, is that x0 prime now is x plus, it is the transform 1, x1 prime is x minus, and eta now in this coordinates, eta plus plus is equal to eta minus minus, and it is 0, and eta plus minus is equal to eta minus plus, and it is 0. Okay, so mu and nu now take values plus and minus. This matrix now is off diagonal. Okay, it's not this part x2 and x3 is not affected, but here we have 1 1 0 0, because this is 0 and this is 0. So in this coordinate system, the Lorentz transformations have a different expression. They are the same transformations, but in different coordinates they have different expressions. And of course, if we go, as we will go at some point, to spherical coordinates, they will have even a more different expression. But here in these light cone coordinates, they take a very simple expression. So these transformations will be x plus prime, x minus prime, equal to some matrix A, B, C, D, x plus and x minus. And all we know is that x2 with the 2, if you want, x plus prime, x minus prime will be equal to x plus to 2x plus x minus. Of course, the factors of 2 do not matter, so we only want to study this relation. And this is a x plus plus b x minus times c x plus plus the x minus equal to x plus x minus. So now the coefficient of x plus squared is 0 and the coefficient of x minus squared is 0. This means that a times c is 0, b times d is 0, and bc plus ad is equal to 1. So in order to solve these equations, we have to take into account that this matrix has to be invertible and also connected to the identity. So the determinant cannot be 0. And the only solution that you have of these 4 conditions is that b and c are both 0. Okay, and you stay with a times d equal 1, and a convenient parameterization of a and d is that a is equal to e to the phi, okay, phi some real parameter, so d is the inverse, it is e to the minus phi. Okay, so this means that the transformations are x plus prime is equal to e to the phi x plus, and x minus prime is equal to e to the minus phi x minus. So these are Lorentz boosts expressed in light cone coordinates. Okay, now you can undo this transformation. You can go back to x0 and x1. So x plus prime will be 1 over square root of 2 x 0 prime plus x1 prime and so on, and you just operate, and what you find is that x prime 1, in terms of this parameter phi, is the hyperbolic cosine of phi times x0 plus the hyperbolic sine of phi times x1, and sorry, this is x0 prime, x1 prime is the hyperbolic sine of phi times x0 plus the hyperbolic cosine of phi x1, or that the matrix lambda that we found before has this form: cos phi, sin phi, and sin phi. Okay, now you compare this matrix with or this transformation with the standard form of the transformation that we found before, and just by the direct comparison you find that the hyperbolic cosine of phi is 1 over the square root of 1 minus v divided by c squared, and the hyperbolic sine of phi is equal to minus v divided by c. Okay, that this is really the hyperbolic, that 1 over the square root of 1 minus vc squared is really the hyperbolic cosine of phi, and that this is a hyperbolic sine of some phi. You can check by checking the fundamental property that the hyperbolic cosine of phi squared plus the hyperbolic sine of phi squared, sorry, minus, of course, this is equal to 1, which is trivial. Okay, this looks like a rotation, and we said that these Lorentz transformations are a special kind of rotations, but rotations that preserve not the unit matrix, but that they preserve something else, this eta. Okay, this two-dimensional part preserves only this part of eta, two-dimensional eta, because here we are not playing with the directions 2 and 3. So this is the group 011 instead of 1, 3. And you see that this group is really isomorphic to the group of the real numbers, because all these transformations are parameterized by a single parameter, phi. These are some rotations, but they are hyperbolic rotations, so instead of cosine, sine, minus sine, cosine in the matrix lambda, you have plus everywhere. Okay, this is a typical group isomorphism, so many groups have different representations. As a matrix group, it is 011, but this is also analogous to the group R. Okay, and also R is isomorphic to R plus if you go from phi to the phi, because only this positive number really plays a role. Okay, when you multiply two of these phi's, which happens in R plus as a multiplicative group, you add the value, the exponents, and this is R as an additive group. Okay, but they are both isomorphic to 011. Okay, now that we have the form of these boosts, it would be nice to know what is the most general form of the Lorentz transformation when the velocity, direction of the velocity of one reference frame with respect to the other is arbitrary and without the extra rotation, assuming that the axes are parallel. Okay, so suppose that the velocity, instead of being just v1, 0, 0, is some generic vi. It is almost an exercise to rewrite the original transformations for this VI. The only thing that you have to do is to understand that you can use VI to project the general formula in directions parallel to the speed, to VI. You just multiply by VI divided by V, where V is the square root of VI, so the absolute value. And you can also project in directions orthogonal to the speed using this. Okay, and that when you do this, you should recover the original simple result of a boost in the direction 1. Okay, so basically this result that I'm going to write now is an educated guess that you can check. Okay, so these transformations will be of this form. So you have x0 minus vi divided by c xi, and then I will discuss why this is true later, divided by this usual factor, and x prime I is this delta ij minus vi vj divided by v squared times xj plus, so this projects in directions orthogonal to x1, plus vi vj xj divided by v squared minus vi divided by c x0, and all this divided by 1 minus v divided by c squared. These are not yet the most general Lorentz transformations. They are the most general Lorentz boosts, assuming that the axes of the two reference frames are parallel. Okay, but that the speed of one with respect to the other is not parallel to v1, to x1, sorry, the axis is 1, which is parallel to x1 prime. Okay, but that has a completely general direction. So, for instance, if v1 vi only has component v1 0 0, okay, you see that vi xi is equal to we call this v is equal to v x1, which is what we wrote before. Also here you have to consider different cases. So if you take x1 prime, so sometimes I write x prime 1 and sometimes x1 prime. Let me write x1 prime. So what happens for x1 prime? This is delta 1j, which multiplied by xj only gives you x1, minus this is only v1, so you have a v here, and vj times xj gives you v times x1. Okay, and this is divided by v squared, so this is 0. Okay, these two terms cancel, plus v1, which is just v, this still gives you again v x1 divided by v squared, minus vi, which in this case is just v, divided by c x0 divided by the square root of 1 minus v divided by c squared. However, if you consider another direction like x2 prime, see this is delta 2j, so it's only x2 that appears here, minus v2, but v2 is 0 with this assumption. So you only get x2 plus v2 is 0, so the third term vanishes and the fourth term vanishes too. So you get that x2 prime is x2 and the same for x3. So these are the most general Lorentz boosts, but expressed in two reference frames with parallel axes. And finally we can express this maybe in a more intuitive form in this way. So x0 prime is just x0 minus v divided by c x parallel. So this is the component of the position of the spatial position parallel to the speed divided by this common factor. Now the parallel component, this would be x1 if the speed is v1, is x parallel minus v divided by c x0 divided by the standard factor, and in the perpendicular directions nothing happens. So x prime perpendicular is just x perpendicular. This is basically what we have written above, but using vi, the vector normalized by this absolute value to project in parallel and orthogonal directions. They are exactly the same formula. And this ends our discussion of the Lorentz transformations. Now, the immediate consequences of the Lorentz transformations is something that you should know. These are time dilation, what happens with simultaneity, all this, which is the physics of the Lorentz transformations, you should know from your previous courses. And if you don't, then you really should ask your money back in your university. We have reviewed the Lorentz transformations because we wanted to introduce concepts like groups of transformations, etc., and the invariance of the interval, and so on, which we will generalize later on. This is the part that we were most interested in. But of course, you are supposed to know everything about time dilation, space contraction, relativistic Doppler effect, these kind of things. Okay, so this is the end.